As we go through these labs, I assume that the student has had some course on static and strength of materials and a course on dynamics. For example, this problem came from a statics book where the idea was to put a certain friction value between this ladder and the wall and appropriate friction value between the ladder and the floor, and then put a weight on here of a certain value and have the ladder at a certain angle and determine if the ladder would fall or not. Another problem in the book was to put a force against this box and a friction value between the box and the floor, and then determine at what point, with the force located at a certain height from the floor, at what point the box would start to slide, or at what point the box would tip over. And so if I look at those calculations, here are a couple problems from the book. This one was English units. This one was in metric units with the ladder against the wall. Some of the other problems were a box of a certain weight being pushed from a certain height from the floor. Typical type of problems were a wedge problem with the load sliding down that wedge. So we can start to make these problems real, or perhaps more interesting, and take them from statics into dynamics in Inventor Dynamic Simulation. And so this is that same problem from the book, and I've adjusted it for dynamic simulation. Of course, the first time through doing the calculations, it's a little bit slow, but once we've done the calculations, it will play back faster, or we've seen that we can export this to Studio and play it back at any speed that we want in Studio. So we start to tie together some of the different mechanism joints to get the mechanism motion that we are after. I haven't spent a lot of time on the theory because I've assumed that you've gone through a static and dynamics course. But for example, in this engine, as the piston turns the crankshaft, the connecting rod may bend slightly. It may be a very tiny amount, but it may bend slightly. It also has to have a little bit of clearance between the piston pin and the connecting rod, and between the crank and the connecting rod. Otherwise, it would not be able to turn. And so we have to put some real-world clearances, or we should put some real-world clearances into our design. As we're running this analysis, Inventor assumes that that part is perfect, that it doesn't bend. So we're designing some mechanism to transfer a motion of forces and do some kind of work. When we're doing the assembly environment, we're just doing the kinematics, where we're studying the motion without consideration of the forces. And then in dynamic simulation, we are considering Newton's laws of motion. In our mechanisms, we are setting up our joints to remove appropriate degrees of freedom. So any object has initially 6 degrees of freedom. It can rotate around Y, it can translate on Y. It can rotate around X, it can translate on X. Or move in a straight line, it can translate on Z, rotate around Z. So our job is to remove the excess degrees of freedom till we have the mechanism operating with the proper motion. And then we join together the various joints to get the mechanism motion that we are after. As we get more experience with dynamic simulation, we start to consider a different method of putting our assembly together from the beginning. So in this particular example, I have this part is a grounded part, and then this part is grounded, and I'll start to assemble some components to this component. And typically what we'll do is we will mate these so that they are right against each other. So we might use an insert constraint or an axis to axis and then a face to face. But in the real world, if we don't allow a little bit of clearance in between these faces or some lubrication, there will be a lot of friction between the two components, making it difficult for them to move. Now typically we would also put a pin in here. We may cheat when we're in the CAD program and not even bother to put the pin, but of course we would have to have a pin in here to hold these two components together. In the same way down here, I have 3 components. I haven't put any clearance between those components, but in the real world we should probably allow for some clearance or lubrication between those components. And then we may do the same thing on the other side, where we put everything up against the faces without any clearance, and we might make a pin without any clearance between the hole and the pin. And in this case, I've exaggerated the clearance between the pin and the hole so that we can clearly see it, but a lot of times we model something without any clearance when we really should. Now this should have at least a tiny amount of clearance between the pin and the hole so that the mechanism can work properly. And the same way down here with this pin, I have some clearance between the pin and the hole, and I've exaggerated that clearance. And then if we might put one face of this up against the component, or this pin might even be part of this component or one of the other components, but we have to allow some clearance, and then there has to be some clearance motion along this axis. So I've greatly exaggerated this, but for the clearance in between these components, I'm representing that little bit of motion that could occur translationally along this axis. That has to be a little bit of clearance, or otherwise the mechanism would bind as though these parts were welded together. And then down here I've represented a second type of motion, and that is that we have to have some clearance where this pin can actually rotate along X, Y, or Z, or if this pin is connected to that. In any case, maybe this part will be able to flex, rotate around its axis this way slightly. Now I've really exaggerated that motion so that we could clearly see it, but we have to have that clearance in here. And so in the CAD program we can fudge these just like not putting a pin in here, but we need to account for the realistic motion, or otherwise we will get an over-constrained condition in dynamic simulation. Now we could do 3D contacts between these. So imagine I had this pin was much bigger but it's still smaller than this hole. So I could do 3D contacts between all the pins and all the holes, but that would mathematically be expensive to do the computation. So there are other tricks that we can do as we assemble our components to not over constrain the mechanism and allow the mathematical computation of clearances between the components. So when we go into dynamic simulation, I have put a spring force in between here and here, and we'll see how to do that in a few minutes. And I've also put a force pushing down on the top up here. Let's go ahead and suppress that force for now, and then I'm going to suppress the spring force as well. So I'll suppress that. And so if I go ahead and play this, gravity takes this part down until it comes in contact with this part. I have a 2D contact between those components. Notice I've also traced the position of where this point moves, the point right in here. And let's play that again. So I see the trace of that point, or any point on here. If I want to trace that point, we'll see how to set that up. And I'll go ahead and put the spring on. So I'm going to unsuppress the spring. And now when I play this, that spring balances that mechanism right in the position where it's at right now. So there's just enough force on that spring to balance it, and we'll see how to set that up. Now if I drag this though, I can overcome that spring force by adding additional force, pulling down on the mechanism. Or I can add a force on here through the software rather than manually pulling on that. If I unsuppress this force, and I'm going to edit that force, and so I have it set in the input grapher, and I have it start at 0 force and then go to 10 newtons over 1 second. Play this again, and it's slowly pushing this pin down. It may not push that linkage down all the way to the table, but we see that force. Now if I increase that force, it's gradually increasing. It may overcome the spring force and push this all the way down. It depends on how much force I put on here. Now we may want to graph that in relation to the position of this point, or a point up here, or a point down here. And so we're going to see how to set that up, where normally on our graph we graph relative to time, but time might not always be what we want on our x-axis. In this case, the distance traveled might be what we want to see on our x-axis. if I drag this mechanism so that it's down against the table. Of course, we've seen how to set up that resistivity for the bouncing, and I will then play this again. We see that the downward force at the beginning, it was not enough to keep this down, and then the force increase. Remember, we graphed that from 0 to 10 newtons over 1 second of time. So a lot of variations that we can put in here for our 4-bar mechanism, and the mechanism could take a lot of different configurations depending on our application. So let's look at how to set this problem up. I'll put a link for the parts used in this demonstration in the description of the video. So I have this part down here is grounded. I'm also going to ground this part. So let's right click and ground that part into position. And then if I move this one, I see that I need to constrain that one. And so typically we would do an insert constraint on that. So we could either do 2 make constraints or 1 insert. So I'm going to do insert, and I'm going to insert this circle onto this circle. Now if we want to, we could go ahead and put in an offset in here. I'm going to put a tiny offset, let's say 0.01 as offset. And then if I drag this part, the same situation, so I'll do constrain and I'll do insert this face onto this face, and I'll do the 0.01 offset on that. Now for what we're doing, it doesn't matter if you do the offset or not. If I try to drag this, I have 1 degree of freedom, rotation. I try to drag this one, I have 1 degree of freedom, rotation. And if I go into dynamic simulation, we would expect 2 revolution joints. And so that's what we have, those 2 revolution joints. Let's go ahead and save this. Okay, then I'm going to go ahead and put a revolution joint between these 2 components as well. And so I could do that right here in dynamic simulation by doing a constraint, and I'll do insert, and I'll say do insert this circle onto this circle. We'll say OK to that, and we see it converts that into a revolution joint. Alright, now typically what we might do is we might constrain this onto this as an insert. So I'm going to do constraint, and I'll do insert, and I will select this circle, and I will select this circle, but I need to put in my 0.01 offset. And we see that that is converted to a revolution joint. And then we may do it again down here. So I'll do insert, I'll select this circle, and I'll select this circle, and I'll do 0.01, and we see that it moves it into position. But it gave me a point line constraint instead of a revolution joint. So I'm going to undo that, and I'll go to the assembly environment, and I'll constrain that. So I'll do constrain, insert this circle onto this circle with the 0.01 offset. We check it out, the mechanism moves, and I'll go to dynamic simulation. And I was actually expecting it to do a revolution joint that time and give me an over-constrained condition. So let's try doing this in a different way. So I'll finish this, and I'm going to undo that last constraint. I need to go back one more. Okay, so that's not constrained. I'm going to change these other constraints so that there's no clearance for those insert constraints. So I'm going to change this one back to 0. Okay, so now I've got all of these changed to 0, and I'll do my constraint, insert this circle onto that circle, and say OK to that. So in the assembly environment, everything works fine. But if I go into dynamic simulation, I was actually expecting it to give me an over-constrained condition. Well, I'm going to set this up slightly different anyhow. So let's delete this constraint, and I'm going to delete this one, and instead I'm going to put axis to axis on this one. So I'll constrain, I'll select this axis, and I'll select this axis, and I'll say OK to that. So this part could slide back and forth slightly, and that is more like in the real world where we'd have a little bit of allowance for that to slide back and forth on the pin that goes in here. And then I'm going to allow for twisting so that it could twist slightly. It wouldn't twist very much, but it would be able to twist slightly. So I'm going to do that as a constraint. I'll select the center point. So if I select a circle, it'll find the center of that circle, and I'll select the center of this circle. And so that gives me 3 rotational degrees of freedom for twisting. This gives me 1 translational degree of freedom for moving back and forth slightly. So that would be more realistic representation of what we would see in the real world. All right, then we'll go to dynamic simulation, and we see then, so we have a cylindrical joint up here, and we have a spherical joint down here. Rotation and translation up here, 3 degrees of rotation relative to this between these 2 components at this joint. So if you get an over-constrained condition, those are the types of ways that you will overcome that over-constrained condition. And it starts to then affect the way you make your assembly in the assembly environment to make sure that you don't end up with an over-constrained condition. I'll then do constrain, and I'm going to do insert this circle on the back side there with this circle. And if you want to put in an offset value there, you could do an offset value. And then I need to mate these so that this one stays lined up with this one. And so we have to be careful with that. If I go to dynamic simulation, I don't want this to become over constrained. And so if I do an angle between this and this, it will probably become over constrained. But if I'm going to do a constraint, if I select this line and then I select this plane, that line could move anywhere on this plane, but it would stay lined up with that. It would stay planar on that plane. And so I'll say OK to that. So we have a line plane joint. That lines those up without it becoming an over constrained condition. Alright, then I want to set a certain height above this, so I'm going to do constrain, and I will select the bottom of this part, and I'll select the top of this part, and I'm going to put in an offset distance for a home position, let's say of 20 millimeters, and I'm going to name that home position. And then I'm going to set that as, use that as the resting position, and then I'll say maximum is 20 millimeters, minimum is 0 millimeters. So now if I drag this and it stops when it gets down to 0, if I let go of it, it goes to that home position of 20 millimeters above this face. Alright, then we'll go back to dynamic simulation, and I want all of these positions where they are right now to be my 0 positions. If I right click on this revolution joint and I go to properties, and it's 1 degree of freedom revolution, because I imported this as a step file, it shows the angles in radians. Let me show you how to fix that. I'll finish dynamic simulation and I'll go to tools, document settings, and I'll go to units. And so for the angles, I'm going to set to degrees instead of radians. For the mass, I'll set for kilograms, length millimeters times seconds. Alright, now when I go back to dynamic simulation and I right click on this first joint and go to properties, I see that its home position is at 0 degrees. And if I go to each one of these and I go to this one, its home position. Now if I wanted to rotate this, I could go ahead and say move 10 degrees if I wanted in a different position. So I'll check this one, home position is 0. So this one has 2 degrees of freedom, a translational degree of freedom and a rotational degree of freedom. And let's actually double check that. So I want to make sure that this thing will work properly. I try to drag it from side to side. So even though it has that translational degree of freedom, it doesn't translate because of the constraint that we have down here. And then likewise, this one doesn't rotate because of the translation constraint that we have up here, although in reality it can rotate slightly about the pin. And when I say rotate, I mean twist around this long axis, but we've constrained that without over constraining it. mathematically. I'm going to put some work points on several of these components, so I'm going to right click and edit this part, and then underneath points I'm going to do a point at the center of a loop, and so I'll select this loop. It'll put a work point at the center of it, and I'll do the same thing down here. So I'll do point at center of loop, and so I have a point here. I'll return, so I'm putting these in the part level, not at the assembly level, and so I will open up this part, or just edit it, and then we'll do point at center of loop, and this is the same part twice, so it also put it down in that part. I'll click return, and then I'll put a point in the center of that loop. So let's open that one, and I'll do a point center loop of edges, and so I've got a point in the middle of that one. I'll save it, go back to my assembly. Alright, then I'm going to go back to dynamic simulation. I'm going to put a spring in between here and here, so I'll do a spring joint, and I'm going to select this point as my first point, and then I'll select this point as my second point, and I'll say OK to that. Now that puts the glyph in for the spring, but it doesn't yet put our spring in there just yet. And let's also define gravity. So I'll go to my external loads, and I'll say define gravity. I want gravity perpendicular to this face pointing down, and if I play this right now, the assembly just goes right through that. So let's put in the 2D contact between this part and this part, so we can either do 2D or 3D. This stays in one plane, so we can do 2D, so I'll do a 2D contact, and I'll select the side of this face. Remember that, think of that like a box surface that goes infinity perpendicular to that face. And then for the second face, I'll select this face, but there is the circles in here and the outside loop, so we need to tell it we want that outside loop, and we'll say OK to that. And then if we'll go to the properties, we could change this restitution and friction, let's say maybe 0.5 on this. Play this again, and it went right through, but notice when it came back it hit against this and stopped. Let's do that again. So it went right through, watch it comes back. It hit it, and then it went back that direction. So here's what's happening. At the precise point where this came down here, where it would have contacted that, it wasn't doing a calculation. So we need to do more calculations. Let's look at a couple different things here. I'm going to go to the output grapher, and I have it set to this precise events, which we haven't looked at yet, but it is set to pick up precise events, but it didn't pick up that contact. Let's increase this, say, to 250 calculations instead of 100 calculations. So now it picks up that contact and it stops. Earlier I was going through these joints and I forgot a step. So we did the cylindrical. We went to the properties, and we saw that the initial position was 0 for the rotation. The initial position was 0 for the translation. Let's go to the spherical. I'll go to the properties, and the initial position is 0 on this one, 0 on this one, and 0 on this one. And we'll go to this revolution. I'll go to the properties of that one. Alright, so I see this one is minus 180 degrees. Now if I type in 0, it's going to move this mechanism 180 degrees. Now rather than type in 0, I'm going to right click here, and I'm going to set offset. So that sets this position as 0 without moving it to 180 degrees by setting that offset. And then I'll come to the next one. I'll go to properties, and it's at 0. And the last one, I'll go to properties, and so this one's offset, this one's offset, this one's offset, and this one's offset. So we could right click and set offset on all of these, but I'm going to show you a faster way perhaps to do it. So if I know that I want all of these positions as my 0 positions, if I go to the simulation settings, and I can tell it to set all of these positions as 0. Now there's also one that will reset, so this would reset it to where it is, where it happens to be now. I'm going to tell it to reset everything. I want its position right now, I want everything to be 0. I'll say OK to that. Now I have set those offsets for all of my positions. Alright, let's edit the spring. So I'm going to go to the properties of that spring, and I'm going to tell it a stiffness of, say, 1 Newton per millimeter. So if it compresses 1 millimeter, it'll put 1 Newton force, or if it stretches 1 millimeter from where it is now, it will put a 1 Newton force. Inventor automatically measured the distance from here to here and put that in as its free length. Let's call this 68. Let's say I wanted a 2 millimeter preload on here. So if I put this in as 70 as the free length, it has to be compressed to plus a little bit 2 millimeters to put in here. That would put a 2 Newton force preload because we partially compressed that spring when we put it into the assembly. But we'll leave it right now. We're going to leave it at the default value, the distance from here to here. And then I could put in a dampening value. I'm going to do 0.1 so that the spring doesn't bounce a whole bunch. Now this is just a visual representation. Don't think of this as a physical spring here. To make it look good, I'm going to change that radius, say, to 1 millimeters, and I'll hit the tab key, and then I'll change the number of facets to 10 is the highest number that you can put it. I'll say do 10 turns, and then for the wire radius I'll do 0.5 and maybe a little bit bigger than that. I might do this is 1.5. I'm just trying to visually make this look good, and I'm going to put this back to 0.5. Alright, so I have the visual representation of my spring force. If I want to change the color of that spring, I can set it to whatever color I would like. Now that is the color when it isn't highlighted. When it is highlighted, it will change to whatever the highlight color is. I think that's everything I wanted to set in here. The spring though is going to hold this into position. If I play this, it may slightly drop, but the spring is holding it in position. So let's put an additional force on here to push this down. So I'm going to go back to construction. I'll do force. I'm going to put that force at this point. I want to set the direction perpendicular to this face. I want it going in the opposite direction, so I'll have that going down. Now this part is going to stay straight up and down, but as it rotates around here, in some cases we may want the force to rotate around an axis, in which case we would set it an associative load direction. In this case I'm going to leave it as a fixed load direction going straight down, and I'm going to put the input grapher. I'm going to say start out at 0, so we're not putting any force on it, and then let's increase that over 1 second. At the end of 1 second, we're putting 10 newtons of force on here to overcome the spring force. And now I'll play this. So it starts to push it down. Now let's go to the output grapher, and I'm going to expand one of the joints, and I may want some information relative to one of these joints, and I need to find which one is which. So I see that this cylindrical joint is this one up here, and I might want some information relative to that cylindrical joint, and so I'll go to cylindrical joint, and I may want the position or the velocity or a force amount or an acceleration that's given over time. I might want that relative to position though, rather than time. I'm going to put a trace at this point right here, and then I'm going to set this to calculate the trajectory. So this will display the trajectory, this will do a calculation, so I want to keep a record of that position. So I'll apply that, and then I'm going to select this point and with the trajectory. Thinking maybe with this point and this point might be two better points. It'd be the same kind of thing. So I'll select that, I'll say OK to that. And let's do these two up here as well. So I'm going to do trace, and I'm going to select this point, and I want to calculate the trajectory of that, apply that, and I want to get this point and calculate the trajectory of that point. Now we calculated the trajectory of this point even though this point doesn't move, and we'll see why in a minute. So if I go ahead and play this again, and I don't need to finish it, but we can see it tracing the trajectory of this point, this one, and I come over here and I see that I have these traces that it has calculated, trace 1, 2, 3, and 4. I will also put this formula into the description, and I've opened it up in Notepad. I'm going to highlight this and Control-C to copy this to the clipboard. And so this is just Pythagorean's theorem, the distance formula, the distance between 2 points in the x direction and in the y direction and in the z direction. I will then tell the inventor to create a new curve, and I'm going to call this ram distance. And then I will click in this white area and I'll Control V to paste that formula that we put on the clipboard. Now if the formula is not valid, it will be in red instead of black. In this case it's black, and this tells us that's a valid equation. And notice this is the distance between trace number 1 and trace number 2. I copied and pasted that rather than type it in because the slightest syntax error would give you an error in the equation. I'll say OK to that. And then I'm going to create another new curve, and this time I'm going to call this spring length. But remember, spring length was between 0.3 and 4. So I need to do x 0.3 and 4. I need to do y point trace 3 and 4. And I need to do z trace 3 and 4. And be careful you don't change the squared, so this value squared will give you absolute value. I'll say OK to that. So I may want this force relative to the spring length or relative to the distance between here and the table. And so I'm going to uncheck these two curves that we just created, but I want, say, the spring length to be on the x-axis instead of the time. I'm going to right click on spring length and I'm going to set that as the reference. So now that shows the force at this joint relative to the spring length, or I could set it relative to the ram distance. I'll set that as the reference. So the 20 millimeter motion from here to here. I'll go back to the spring length and set that as reference. So the spring changes from about 60 millimeters, and actually as it's going down it compresses, so it's going actually from 68 millimeters down to about 60 millimeters. So you see how we can start to gather some information from the output grapher. We've seen how to put values in with the input grapher, and then taking care not to get an over-constrained condition on our mechanism. I really intended for this one to give us an over-constrained condition. Inventor was smart enough though to avoid creating the over-constrained condition in this case, but that's going to be your biggest issue as you add more and more joints to a mechanism, is avoiding an over-constrained condition. The easiest way to avoid an over-constrained condition is with an understanding of how the various constraints will be converted to joints as you go along.